This week's theme is the importance of the electron. You've seen models like this before, and I've told you if it has a cap on top, it's a negative ion. Negative ions can be represented like so. Cl is the symbol for chlorine, but if you put the negative, that's an ion. The name of this ion is chloride. You've seen it many times: sodium chloride, calcium chloride, copper chloride. This chloride ion can be thought to be made up of two parts. There's the Cl atom, chlorine atom, and then this part is an electron. Electron, represented as E with a minus. So a chlorine atom plus an electron can turn into a chloride ion. Negative ions that you've seen previously all have these caps, which you can think represent electrons. This is sulfate. It's a -2 ion. It has two caps, two electrons. This is nitrate, -1, has a single cap. Carbonate, -2. Positive and negative ions can bond together. If that's a copper +2 and a sulfate -2, they make copper sulfate, a compound, an ionic compound. And you know negative ions can't bond to each other. Negative doesn't attract negative. Here's another way of modeling the importance of the negative. This is a chlorine without a charge. This is chlorine with a negative. This is the one that can bond to a positive ion. Today, and this whole week, you're going to see a new kind of model. This is going to represent aluminum. Aluminum has the symbol Al. You've seen aluminum many times in your life. This is not a negative ion. Metals such as aluminum, magnesium, copper, etc. can never be negative. But the aluminum metal does have electrons that are exceedingly important. So aluminum atoms can exist in this form or this form where they've lost their electrons. The form that has lost its electrons is an ion. It's a positive ion. So this can represent aluminum with a +3 charge. This represents aluminum with no charge. Aluminum with a charge doesn't look anything at all like aluminum without a charge. The aluminum ion makes salts. Aluminum with no charge is a metal. The salt I'm using as an example is aluminum nitrate. That's what this is here. And this should make sense to you because aluminum as an ion can bond to things that are negative, like nitrate. So 1, 2, 3 nitrates, each one with a -1 charge, balances out the aluminum with a +3. This is a compound. It's aluminum nitrate. Aluminum with no charge can't bond to nitrate, can't bond to sulfate, can't bond to carbonate, can't bond to anything. It remains alone. This is pure aluminum. This is a compound. In many reactions, electrons move. In today's reaction, you will see there's a time when you start with aluminum that looks like this, but those electrons will come off. And you will be left with aluminum that does not look like the metal anymore. Instead, looks like the salt form. Those electrons need to go somewhere. So I'm hoping today you'll be able to figure out where do these electrons go. It will explain the chemistry you observe in today's experiments. My model for electrons has one very big weakness, and it makes it seem like the electrons have a lot of mass. In reality, electrons have very, very small mass, almost zero. The periodic table will tell you that the mass of aluminum, the atomic mass, is 27. The aluminum ion is the same. So although the models will have different masses, the reality is that the ion and the neutral atom have the same mass.